Hi everyone, this is Dr. Sandeep, working as Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. Today we are going to discuss about the Gibbs phase rule for the construction of binary phase diagrams. So in the previous sessions we have seen what are the phase diagrams, what are the importance of phase diagrams, how to draw these phase diagrams. And in this session we are going to discuss about the Gibbs phase rule. So we have to follow some rule in order to draw these phase diagrams. So what are the rules we have to follow while drawing the phase diagrams can be described with the help of this Gibbs rule. So we'll discuss this Gibbs rule for drawing the binary phase diagrams in this session. So the main important of this Gibbs rule give us the relation between the number of phases, the concentration as well as the externally controlled variables. So all these things combinedly give the relation between all these things with the help of this Gibbs phase rule. Now if you see this, the Gibbs phase rule, the construction of phase diagrams as well as some of the principles of governing these equations will be done with the help of the thermodynamics laws. Okay, so what are the phase diagrams we are drawing? These phase diagrams can be drawn with the help of the laws of the thermodynamics with the help of the some of the variables. So what are the variables we will see in the coming sessions. So this rule, so what are the Gibbs rule we are seeing? This Gibbs rule represents the criteria of number of phases that are present within a system. So if you want to find out the number of phases present within the system can be developed, can be calculated with the help of this Gibbs phase rule. And we have a simple equation for this Gibbs phase rule as P plus F equal to C plus M. So what is this? P plus F equal to C plus N gives the Gibbs phase rule. Gibbs phase rule. Okay. So this Gibbs phase rule is helpful in construction of the binary phase diagrams, and this Gibbs phase rule gives the relation between the phases. So what are the phases we have? The number of components we have, or number of the externally controlled variables. So all these come together and will give the Gibbs phase rule in order to construct the phase diagrams. And also this phase diagram will tell us how many number of phases are present within the system. So how many phases are present or how many phases are existing in the present system can be done with the help of this Gibbs phase rule. Suppose in any system you may have a number of phases. So how many number of phases are there can be calculated with the help of this Gibbs phase rule. Okay, whether it may be a single phase or double phase, but it will give the number of phases existing within the system. Now here each thing we'll see here in the relation of Gibbs phase rule, P plus F equal to C plus N. So what are the each notations we'll see here? So the first relation in this we'll see what is P. So what is P we'll see here. The first one, the P is the number of phases present. Okay, so in this relation of P plus F equal to C plus N, the P represents the number of phases present in the system. Okay, if you want to know how many number of phases present in the system, you need to calculate the other three things which are there in this Gibbs phase rule. If you know what are the values of F and C plus N, then it is very easy for us for calculating what are the number of phases or how many number of phases present or existing in the system. This parameter P is called the number of phases present in the system. Next, what is the other term you have? The F. The second term is F. F is termed as the number of degrees of freedom or number of externally controlled variables. Okay, so here P is nothing but your phases, number of phases present. And coming to the second parameter, so what is the second parameter we have? F. So this F represents the number of degrees of freedom. Degrees of freedom, or what is the other thing we have here? Number of externally controlled variables here. externally controlled variables. So what are the externally controlled variables we have here? The temperature, the pressure, as well as the composition. So in the earlier sessions we have seen in the phase diagrams, so what are the important criteria or important parameters we need to draw the phase diagram is, we need to require the temperature, the pressure, as well as the composition. So these three items or these three parameters we can control externally. I can increase the temperature or I can decrease the temperature. In the same way, I can increase the pressure or I can decrease the pressure, and also I can vary the composition of the materials. So these are the three parameters which I control externally. Okay, that's why this F is called it is the number of degrees of freedom or the number of externally controlled variables in the Gibbs phase rule. So like that, if any one parameter, if you want to know, the three other parameters we have to know. Okay, so if any one parameter you need to identify, these three parameters we have to know. So that is the case of the Gibbs phase rule and the importance. And in this case, what we'll see, these three parameters which are being controlled externally must be specified to completely define this system, the complete system, is it not? If you want to define a complete system, we need to know, we need to specify all these three parameters, then only we can specify the system. Now, this expressed, the F value can be expressed as the number of these variables that can be changed independently without altering the number of phases that coexisting in the equilibrium. So what is happening here again? So this point we need to take into consideration. What is happening here? What are the F we are taking? That is the number of externally controlled variables. These variables then can be changed independently. So these can be changed independently without altering the phases. So that is a very, very important thing we need to find out here. So what are the three variables we are taking into considerations? So these three variables are externally controlled, but these can be controlled or these can be changed within themselves independently without altering the phases which existing in the system, and this should be at equilibrium. So that is a condition we need to take into consideration while controlling or while changing these externally controlled variables like pressure, temperature, as well as the composition. And coming to the third parameter, in this case, the third parameter what we have? C. So C represents for the number of components in the system. Number of components in the system. So number of components in the system means, in the previous cases we have seen some examples of water and sugar. Water and sugar we have taken some of the example, and aluminum and silicon also we have taken example. So here how many parameters we have? In this we have two parameters, in this also two parameters. So how many parameters are existing in the system? So that also we have to take into consideration. So that is the C value, whatever the in the Gibbs rule or Gibbs equation we have. So this C represents for the number of components present in the system. So components are normally the elements or stable compounds in the case of phase diagrams, and the materials at the two extremities of the horizontal component. So in the phase diagram, what we are trying to do, so this is the phase diagram axis. So along x-axis we are drawing the composition. Along the y-axis we are taking the temperature. So in this case, of course it starts with 0 and ends with some 1000 degrees centigrade like this. And in this case, if I have two elements, if I take a silver and aluminum, okay, so what happens here? This starts with 0% and this starts with 100%. And coming to this, what is happening here? The silver reaches to 100% and aluminum reaches to 0%. So this is the composition. Now, how many components are there at the two extremities of the horizontal? So here, if you read this line, the materials that two extremities of the horizontal composition. So this at this point and this point, two extremities of the horizontal. So how many are there here? Two components are there, aluminum and silver. So total two components we have. So like this, we have to calculate how many components are present in the system so that we can take the value of that component in this Gibbs phase rule and identify any one of the things. And finally, what is the third term we have here? Third term is your n. Sorry, fourth term is your n. So what is the n here? Number of non-compositional variables. Non-compositional variables, what is have? So totally in this we have 3 variables. So what are the 3 variables we have here? So total 3 variables we have. 3 variables. So in these 3 variables, what we have? Temperature, pressure, and composition. Now coming to n, so what n is telling us here? N is the non-compositional variable. So in these 3, which is the non-compositional variable means what? Only this composition is composition. The other temperature and pressure are not compositions here. That's why what are the non-compositional variables here? You have temperature and pressure. So n refers to your temperature and pressure because n is a non-compositional variable. So in these 3 variables, n refers to the non-compositional variable. So what is the non-compositional variable? We have to neglect the composition variable here. So other 2 is what? The temperature as well as the pressure. So n value we have to take as 2 in this case. Now if you take an example and if you try to solve the Gibbs phase rule, how many phases are present, or if you want to find out how many parameters are there, okay, which are the externally controlled variables, or the number of n value if you want to find out. So it is very easy for us to take some example and we can define this Gibbs phase rule by considering an example. So we are demonstrating a phase rule by applying it to a binary temperature composition phase diagram. So in this case, we are taking as copper and silver as an example. So copper, silver as an example. Here what is happening here? Because pressure is at constant and the parameter n in the term is the only non-compositional variable. So what is happening here? Since the pressure is constant here, the parameter n, what are the parameter n we have? The fourth term P plus F equal to C plus N. So n value we are taking as temperature and pressure. But pressure is constant value. That's why this n value, actually it has to be 2. But since the pressure variable is a constant here, so only we are taking n as 1, that is the temperature. So this is the temperature, n equal to temperature. So what we are getting here? P plus F equal to C plus 1. Now furthermore, the number of components in this, how many are number of components we have here? Copper and silver we are taking. So there are 2 components here. Therefore, the value of C will go with the 2. That is, the number of components which are present in the system is 2, that is the silver as well as the copper. So P plus F equal to C we are taking it as 2, so plus 1, so that is 3. So P plus F equal to 3. So we are just rewriting this equation as F equal to 3 minus P. Now consider for the single phase fields of the phase diagram. What are the single phases notations we have here? The alpha or beta or the liquid state. So these are the 3 single phases which are available in this example we are taking. So we are considering the case of a single phase. Either it is a alpha, beta or liquid phase. So earlier we got this F equal to 3 minus P. Now the P is nothing but the number of phases present. So just replace this P with 1. So how many are getting? F equal to 3 minus of P, that is 3 minus 1 equal to 2. So therefore F is what? The number of degrees of freedom, or F is nothing but the number of externally controlled variables. So how many externally controlled variables are required here? 2 externally controlled variables are required for a binary single phase system. when there are two components in this. So like that, you need to find out how many degrees of freedom are required to describe a phase diagram in a binary system which is having two components. So that means to completely describe the characteristics of an alloy that exists within a system of these phase fields, we must specify two parameters. So what are the two parameters here? These are the composition and temperature. So this is very, very important in describing any phase diagram with the help of this Gibbs phase rule. Now with the help of this Gibbs phase rule only, we can able to find out how many parameters are required to describe this a binary phase system or to construct a binary phase diagram. Okay, so with the help of these parameters. So that's why in this case, if it is a single phase which is having a two component system, there are two externally controlled parameters are required to describe the characteristics of the alloy which is existing in the system. In a similar case, in the same way, if you take instead of a single phase, if you take a double phase, so what happens we will see. That means if two phases are existing within a system. In the previous case, what we have taken a single phase existing in the system. Now, for the same two component system, if two phases exist, that is the alpha plus L, beta plus L, and alpha plus beta. If any two phases exist within the system, what happens? What happens to that degrees of freedom, that is the F value? So we have that general equation from the Gibbs phase rule as F equal to 3 minus P. In the earlier case, P we have taken as 1. Now in this case, since we are taking as two phases existing, so P we are replacing with 2. So therefore, we are getting F equal to 1. That means what? Either any one parameter of the composition or the temperature is required to describe the characteristics of the alloy existing in the system. Okay, here F is equal to 1. That means either temperature or composition is required. Any one is required from temperature or composition to describe the characteristics of the alloy which is existing in the system. If it is a two phases, if it is two phase in the binary phase diagram. So that is very, very important here with two phases. Okay, and the same way, if it is a single phase, F is equal to 2 when if it is a single phase. That means here two parameters are required. Both the two parameters are required, that is the temperature as well as the both composition is required to describe the characteristics of the alloys which is existing in the system for the single phase. And if it is a two phase, only one parameter, either the temperature or composition should be required to describe the characteristics of the alloy which is existing in the system. So that is how you have to follow the Gibbs phase rule in describing the characteristics of the alloys which are existing in the system. And that's why this Gibbs phase rule is very, very important in construction of the phase diagrams for any type of whether it is a binary or unary phase diagram. Now you can take the example again of the iron carbide diagram, that is the Fe3C phase diagram here. Now in this phase diagram also, this is very, very important phase diagram. So this portion of the iron carbon phase diagram represents in this figure, you have a pure iron. You have pure iron. Almost it is similar to the all the phase diagrams what you have considered in the previous sessions, whether it is a silver or copper or aluminum copper or any type of system. In the same way, this iron carbide diagram also the same thing. In this case also we will find out the number of phases present, how many single phase or how many double phase systems are there, and what are the melting temperatures and how these melting temperatures are being reduced with the addition of other elements. All these things we can see. Here the pure iron upon heating, what is happening here? Again, you have on the y-axis the temperature, on the x-axis you have the composition. The same thing we are taking, x-axis composition and y-axis temperature. Okay, so the pure iron upon heating experience two phase changes in this case. So in the previous examples, whatever the things we have taken, if you heat slowly, what is happening? This metal is getting melted and reaches to some temperature. Again, it's fall down to the other solidifications. But in this case, which is having a single crystal structure during the heating process. But in the iron phase diagram, or iron carbide diagram, what is happening here? The pure iron, when you heat, what is happening here? It experiences two changes in the crystal structure. So that is very typical example or the thing in this. If you observe here, what is happening? The pure iron, when you heat, it gets into two crystal structures, two different crystal structures before it melts. So before it melts, what is happening? It is having, or it is experiencing two types of crystal structures. So at room temperature, the stable form, which is called as a ferrite, which is having a BCC. So at room temperature, the basic structure is the FCC, that is the face centered cubic structure, which is called as a ferrite. Now this ferrite experience a polymorphic. What is polymorphic means? Which occurs in different forms, which occurs in several different forms. The polymorphic is nothing but which occurs in the several different forms and transforms to FCC austenite. That means earlier the iron at room temperature, which is called as a ferrite, has a BCC crystal structure, that is the body centered cubic structure, and later on, after heating at 912 degrees centigrade, this BCC converts to FCC, that is the austenite, that is the face centered cubic structure. That is, from BCC to FCC, it is being converting. That's why it is experiencing two changes in the crystal structure. So next, what happens here? This austenite persists to 1394 degrees centigrade. That means slowly, whatever the FCC is there, it persists to 1394 degrees centigrade, and at which the temperature, the FCC again come back to BCC. So what is happening here? Earlier it is BCC converting to FCC, again coming back to BCC. This is at room temperature. This is at 912 degrees centigrade, and this is at 1394 degrees centigrade. So approximately this 28 degrees centigrade. Okay. So the pure iron at room temperature, we are having the BCC type of crystal structure, and slowly if you heat, so this is called as a ferrite austenite. This is called again delta ferrite. So there is a change with respect to temperature. So BCC to FCC and FCC to BCC. So earlier it is called at room temperature as ferrite, and slowly if you heat up to 912 degrees centigrade, it reaches to austenite temperature, and if it's further heated up to 1394 degrees centigrade, it is converting to again to BCC as a delta ferrite. So this is the transformation of the microstructure of the pure iron, if you clearly see in the phase diagram. Okay, so like this it reaches to the 912 degrees centigrade, and again, okay, it retains up to this point as 1394 at this point, and attains at 1538. So like this, what are the thing you are seeing in the red line? This is the transformation of the pure iron from the room temperature to the austenite temperature. So all these changes are apparent along the vertical axis of the phase diagram. So all these things we are showing in the phase diagram on the vertical axis with respect to the temperature, how it is being converting. So that's why the phase rule, the Gibbs phase rule, is very, very important in order to identify the what are the externally controlled variables or how many phases are present. Okay, with the help of these Gibbs phase rule only, we are trying to draw the phase diagram. So here you can clearly see how it is being transforming. So initially it is in the ferrite form, and slowly it is coming to austenite. And if you see here, you can get the delta ferrite. Again, if you see here clearly how many single phases are there here. So this is the single phase 1, austenite is another single phase, gamma is another single phase, the liquid is the fourth single phase. Okay, and yeah, of course, this is the fifth. So total you have 5 single phase. And how many dual phase, double phase? I will take as a Roman number 1, 2, 3. So total 3 double phase. So all of combined 8 phases exist in the system. So total 8 phases are existing in the system, in which we have 5 single phases and 3 double phases. Now the composition axis figure extends only up to 6.70. So if you clearly observe, we are seeing the composition which is ending up to 6.7 only. Okay, Y means 6.7 weight percentage of carbon. So at this concentration, what is happening? We are getting the cementite is formed. So after cementite, slowly it is converted into graphite. So that we'll see in the next further classes. So up to conversion of this iron into cementite. Okay, that's why it's called as iron carbide diagram. So that's why we are concentrating up to 6.7 weight percentage of carbon only. So up to this point only this iron is converting into cementite. That's why you can see clearly it is forming into cementite. Whatever the carbon is there, the pure iron is there. So this pure iron is converting into cementite, that is Fe3C at 6.7 weight percentage of carbon. So up to this we'll end the cementite. Now the iron carbide system can be divided into 2 parts, in which iron rich. So when iron rich is there, that is the one portion, and if it is not there, that is the other portion. So that's why we are splitting this into 2 portions. One is the complete iron, pure iron, another is pure graphite. So pure graphite when you will get when there is a 100 weight percentage of carbon. That means beyond the 6.70, if it is crossing and reaching to 100%, then we are getting pure graphite, and up to 6.70 we have pure iron. So that's why we are dividing this iron carbide phase diagram into 2 parts. One is from 0 to 6.70, that is up to the cementite, and from this 6.70 to 100 we are reaching to the graphite, that is the pure graphite. So 2 portions. So first portion we are seeing in this now. So in practice, all steels and cast irons have carbon content which is less than 6.70 weight percentage of carbon. So what are the cast irons or steels we are existing in our daily life? These have a carbon weight percentage which is less than 6.70. Therefore, we consider only the iron carbide diagram up to this only. Okay, beyond this, if we consider, we are going to the graphite. So we are not discussing about graphite in now. Up to iron carbide only we are discussing. That's why we are closing the phase diagram up to this 6.70 weight percentage of carbon. So in the earlier cases, we have seen up to 100% because there is no differentiation. But here, since there is no existence of pure carbon or pure graphite, so up to 6.7 only it is restricted. That's why we are constructing our phase diagram up to this point of 6.70 only. So now, if you see here, the figure would be appropriately labeled up to Fe3 phase diagram because we are not considering beyond that limit. So conventionally, it is expressed as weight percentage. So we are describing this composition in terms of weight percentage, so that we can easily tell that the composition of these different elements are useful to describe how much percentage of carbon is existing in the system, so that we can easily divide this into two parts, whether it is a pure iron or pure graphite. So again here, carbon is interstitial impurity in iron, which is forms a solid solution with these each alpha and delta ferrites with austenite, which is indicated as alpha, gamma and delta fields. So what are the fields we are seeing here? Ferrite, austenite and gamma. Okay, so all these are the single phases which are existing in the system. And also of course we have the two phase systems also, with the combination of the liquidus as well as the iron. Okay, so this is how you will find out the different types of phases are existing in the system with the help of these phase diagrams. And if you further go depth and if see the complete microstructure, so this is how we can see the structure of these low concentrations of carbon up to before the 6.70. So that's why we have very less percentage of carbon content. We have seen these dark spots. Okay, if you cross beyond the 6.70, again this percentage of carbon increases, so that it will have a pure graphite. So that is the difference between the two portions what we are considering in discussing these phase diagrams. Before 6.70 what is happening, and after 6.0 what's happening. So before 6.70 we have the pure pure iron, so which is having the less percentage of carbon content, and after reaching to the 100% of carbon we have the pure graphite. Again the austenite or the gamma phase of the iron, which can be seen at the 727 degrees centigrade. So this is the line where we can see this line. So in the previous session we have discussed about the BEG curve. So this BEG curve describes how the phases are being changing from the liquid to solid state. Similarly, this line also indicates how the iron carbon are changing from liquid to solid state also we can see. And this is solubility is approximately 100 times greater than the BCC. So in this case, what we are having, the main thing is what? When the pure iron is heated, so this is being converting into two different phases. So from initial state it starts at BCC and slowly it is converting to FCC and again coming to BCC. So this is how there is a change in the crystal structure of this iron carbon also. So this is the austenite phase what we have seen. In the previous case we have seen the alpha phase, and this is the austenite phase. So that is the FCC BCC structures. And the cementite, the third one, Fe3C, that is the Fe3C, the cementite. So in this case the solubility limit of the carbon in alpha ferrite is exceeded below the 727 degrees. So below the 727 degrees only we are getting this Fe3, that is the cementite. And also this gamma phase will also coexisting between these two lines, that is the 727 and 147 degrees centigrade. So this is how you have to find out. And if you see the properties of this cementite, so it is very hard and brittle in nature, and the strength of these steels can be enhanced by the addition of the carbon content. And again in this also we have the two phases. So once the liquid upon cooling, what happens, slowly this liquid converts into two phases. We have some solid as well as the liquid phase also. That is why it is having these two. And the same two phase region, if you heat, it is converting into low. So that's why we are showing like this. Once the liquid is cooled, it has two phases, and these two phases when you heat, it will convert into a single phase, and that is called eutectic reaction. And the eutectoid reaction is nothing but the liquid phase converts into again two solid phases, that is the alpha as well as Fe3C. So alpha is nothing but it is having very less weight percentage of carbon, approximately 0.022, and Fe3, that is the cementite, which is having 6.7 weight percentage of carbon. So this is the eutectoid reaction. So when one solid phase is being cooled or hot, you'll get two types of solids. So that is called the eutectoid reaction. Pertectic reaction is nothing but solid plus liquid. When it is being cooled, it converts into a solid, or this solid when it is heating, it will convert into two components, that is liquid and solid. So this is the transformation of the three reactions: eutectic, eutectoid and pertectic reactions. So these three are the invariant reactions which can be observed in the iron carbide diagram. And These are some of the references books where you can get the information about the Gibbs phase rule. So what is the importance of the Gibbs phase rule, and how to identify these parameters in the Gibbs phase rule, that is the P plus F equal to C plus N, and what is the importance of the Gibbs phase rule in identifying the number of phases present in the system, and how to identify the three externally controlled parameters or the degrees of freedom with the help of these Gibbs phase rule. And this Gibbs phase rule requires the four parameters, that is the P plus F equal to C plus N. So these three parameters are very, very important in order to find out the number of phases present in the system or the number of degrees present in the system, which helps us to explain the characterization of the elements which are existing in the system. So you can find the information from these books, that is Introduction to Physical Metallurgy by Sidney Hefner, and the second one is Essential of Material Science and Engineering by Donald. Third one is Material Science and Metallurgy by Kodigiri, and the fourth one is Material Science Engineering by William Castle. Okay, thank you for the session.
Like, share and subscribe. Hit the bell icon for more updates.